Hey, we have two last things to consider in this, the third of our volume videos. One is what happens if we rotate our region about a vertical line, such as the y-axis, instead of a horizontal line like the x-axis. And the second is, what do we do if one of the radii changes somewhere along the interval where we're integrating? So let's take a look. For our first example, we're going to consider the volume of the solid generated by rotating the region enclosed by the three curves y equals 1/2 x, y equals 0, and x equals 2 about the y-axis. So let's draw a picture. Here we have the line y equals 1/2 x. The line x equals 2 is a vertical line through 2. And the line y equals 0 is the x-axis. And so the region we're talking about is this region here. And if you rotate that about the y-axis, you get this sort of stadium-shaped thing, best I can describe it. And if you started taking thin slices along the x-axis the way we've been doing, they'd be horrible shaped and we would have very little chance of trying to determine what their volumes were. On the other hand, if you take a thin slice along the y-axis, in other words, as if you were going to add these up along the y-axis, it's the familiar washer that we've been looking at, a thin cylinder with a thin cylinder cut out of the middle of it, and we already know the volume of that and how to add them up using integrals. And so the idea in this case is to add up infinitely many, infinitesimally thin washers along the y-axis to come up with the volume of this solid. We pretty much already have a formula for that. It needs slight modification. What we need is to determine what the constants of integration are, so where we're integrating from and to, and then what the inner and outer radii are. And since we are adding these up along the y-axis, we are starting at this point here where y is clearly equal to 0. And moving up the y-axis until we hit this point here, where we have to figure out what the y value is. And that point has the x value too. It's the point where the lines x equals 2 and y equals 1/2 x intersect. And that's when y equals 1/2 times 2, or y equals 1. In other words, we need to integrate up the y-axis from 0 to 1. Since we're rotating around the y-axis, the center of this shape is on the y-axis, and so the radii that we need to find start at the y-axis and then move out until they hit the bounds of the figure. In other words, pick some arbitrary y value, and this line that I've drawn in here shows us the inner radius. It's the distance from the y-axis to the spot where we hit the curve y equals 1/2 x. To find that distance, we can use the same trick we did when we were rotating about horizontal lines and just label the endpoints of that line segment with their x and y coordinates. Now the left-hand endpoint is clearly 0y. We've picked some arbitrary y value. The right-hand endpoint also has y value y, and the question is, what's its x value? In other words, if you know the y value, how do you find the x value of that point? And the answer is, we know that y is equal to 1/2 x, and so x is equal to 2 times y. In other words, the right-hand endpoint of that line segment is 2 times y, y. And if that's confusing, you can think about it with actual numbers instead of some arbitrary y. For example, suppose y was equal to 1. Then what would you expect the x value to be equal to? Well, y is equal to 1 when x is equal to 2, because 1/2 times 2 is equal to 1. And so same idea, when y is equal to y, x is equal to 2 times y. And this lets us figure out the inner radius. The length of that line segment is simply the difference in their x values. Their y values are the same, or 2y minus 0, or 2y. Now we need to compute the outer radius. You pick some arbitrary y value, and we take a look at the distance from the y-axis to the outer edge of this solid. And if we label the coordinates of the endpoints of that line segment, well, the left one is the point 0y for some arbitrary y, and the right one is the point 2y. And so the difference between those 2 points is simply the difference in their x. The distance between those 2 points is simply the difference in their x values, which is 2 minus 0, or 2. And now we're in great shape to compute the volume. The volume is the integral from 0 to 1, because we're going from y equals 0 to y equals 1. Again, we're adding these washers, these very thin washers, up the y-axis, of pi times the outer radius squared minus the inner radius squared with respect to y. And now we've done all the hard work, not that it was that hard, and we're left with a very simple and straightforward integral. And I'll let you verify the steps. We come out with the answer that the volume is 8 pi over 3. Okay, you guessed it, your turn. You're going to find the volume of the solid generated by rotating the region enclosed by y equals x squared, y equals 0, and x equals 2 about the y-axis. I'll help you with the picture. We're talking about this region right here that I've shaded in light blue. And then you have to rotate it about the y-axis. And you get something more or less like that. I'll refrain from trying to put in any three-dimensional shading ideas because it sort of clutters up the picture, and maybe this will help you find the inner and outer radii. So take a few minutes, go from here, see if you can compute the volume of this solid. Pause the video. When you're ready, start it back up. One thing you have to figure out is what are the constants of integration? Well, we're starting at y equals 0 down here, and then we're moving up to whatever the y value is, where the curves x equal 2 and y equals x squared intersect. And if x equals 2, well, that intersects the curve y equals x squared at the point 2, 4, and so the y value that we're talking about is 4. And so we're integrating up the y-axis from 0 to 4. The outer radius for any value of y is always going to be 2, the distance between the y-axis and the line x equals 2. So this is x equals 0 to x equals 2, a distance of 2. And then the inner radius, this distance right here, is the more interesting one. The two endpoints of this line segment have the same y value. It's some y value between 0 and 4. It's changing and we've picked it arbitrarily. And they're going to have different x values. The one that's along the y-axis is going to have an x value of 0. And then the one that's along the curve y equals x squared, well, we have to compute for a given value of y, what is the x value of that point. And once again, we do that by starting with the equation y equals x squared, the equation of the curve, and trying to compute what is x in terms of y. And we can see that x is the square root of y. And if you like thinking about it in terms of coordinates, the coordinates of the left-hand endpoint are 0y, and the coordinates of the right-hand endpoint are square root of y, y. And so the inner radius in this case is just the difference between those x values, and square root of y minus 0 is square root of y. And now we're ready to actually set up our integral. And it's this integral right here. The volume is the integral from 0 to 4, because those are the boundaries along the y-axis that we're integrating, starting at 0, ending at 4, of pi times the outer radius squared minus the inner radius squared with respect to y. And I'll let you follow along the easy calculus and can't even call it algebra, arithmetic there, to come up with that the volume of this solid is equal to 8 pi. Okay, now suppose we take almost the same problem, but we add another curve. We say the region bounded not only by x squared y equals 0 and x equals 2, but also by x equals 1, and rotate that about the y-axis, so that we're now talking about the region, the portion of the region we had before that is currently shaded in light blue right here. From the outside, you can't really tell when you look at it that there's any difference. It looks very similar. But if you could look at it with your X-ray vision, you could see that internally we've drilled out a hole in the center here, and it's that part that used to fill up the area between 0 and 1 along the x-axis is now gone. And so what we want to do is figure out the volume of this new shape. We're still integrating up the y-axis from y equals 0 to y equals 4. And if you look at the outer radius, it hasn't changed at all. It's still equal to 2 everywhere. It's the inner radius where things start to get interesting. And by the same reasoning that we just went through, we get that the inner radius there is the square root of y. The x-coordinate for any given y-coordinate there is the square root of y, and so that's the distance of that line segment. But something changes once we pass y values lower than this point right here, because then the right-hand endpoint of the radius is not determined by the curve y equals x squared, but instead determined by the curve x equals 1. And so in this case, or for this value of y, the inner radius is not the square root of y, it's the length of that line segment, which is the difference between the x values at x equals 0 and x equals 1, because it has the same y value there. And so what we're talking about is a difference or a distance of 1. And how can we have two different inner radii? Well, we do in this case. We have two different inner radii, and it depends on what value of y you pick. In particular, once you pass this point right here, well, the inner radius changes. It changes from 1 below that point to square root of y above that point. And so we need to know what is the y value of that point right there. And that point right there is where the curve x equals 1 intersects the curve y equals x squared. And when x equals 1, y equals 1 squared, or 1. And so that's the y value 1. In other words, the inner radius is the square root of y when we are above y equals 1, and it's equal to 1 when we are below y equals 1. And so in order to figure out the volume of this solid, we need to add the volume below 1 to the volume above 1, meaning we need to compute two integrals and add them together. And the two integrals are just these. The integral from 0 to 1 of the outer radius, which is 2 squared, minus the inner radius, which is 1 squared with respect to y, plus the other half of it, the integral from 1 to 4 of the outer radius, which is still 2 squared, minus the inner radius, which is now the square root of y squared with respect to y. And so computing these two integrals and adding them together will give us the volume. And I've just shown a few of the steps of the work here. There's obviously a lot of arithmetic to do that I've left out. And in the end, you get 15 pi over 2. You're welcome to check. Okay, here's one for you. I'll help you set it up. We're going to find the volume of the solid that we get when we rotate the region bounded by the curves y equals x squared, y equals 1, y equals 4, and x equals 0 about the x-axis again. Here I've drawn the curves y equals x squared, y equals 1, y equals 4, and x equals 0, which is the y-axis. And so the region that we're talking about rotating about the x-axis is this one here in blue. And what does it look like when you do that? Well, from the outside, minus any sort of shading to try to make it look three-dimensional, it looks something sort of like this. But you also have to keep in mind that it has this hole drilled out of it in the middle that I have tried to sketch in. All right, take a few minutes and try to set up the integrals that you would need to compute the volume of this solid. And when you do, don't forget that in this case, we're rotating about the x-axis, not like the y-axis like we've done in the last couple of examples. And so, these washers are going to be added up left to right. We have thin washers going from some x value to some other x value, just like we did in the previous examples before today. So when you're ready, pause the video, or maybe even when you're not ready, pause the video. Pause the video, think about this sum, see if you can't come up with the appropriate integrals, and then when you're ready, you can unpause the video, start it back up again, and we'll see how you did. Okay, as I mentioned, our integrals are going to be along the x-axis, and they certainly start right here, right there at the boundary of our region that we're rotating, and that's certainly where x equals 0. Where do they go to? Well, they go to whatever this x value is, so they'll go to down there, and so we have to figure out what that x value is. And that's the x value where the line y equals 4 intersects the curve y equals x squared. And in this case, you could certainly do it in your head, but in general, you would determine where those two curves intersect by setting them equal to each other and writing 4 equals x squared and solving. And in this case, we get that x is at positive or negative 2, and where the negative answer is not part of our picture, so we're looking at the point where x equals 2. And so this point right here, where x equals 2. The inner radius is the interesting one. If we pick an x value to the left of whatever this point is, then we get this as our inner radius. It's the distance from the x-axis to the line y equals 1, which gives us an inner radius of 1. On the other hand, if we pick an x value a little bit further to the right, then we get an inner radius that goes from the x-axis to the curve y equals x squared. And that distance is the distance from y equals 0 to y equals x squared. Subtract the y values, and we get that the distance is x squared. As usual, if it helps you, you can simply write down the coordinates of the endpoints of this line segment. The bottom one is at x0 for some value of x, and the top one is at x squared for the same value of x. And so that should make it obvious that the length of that segment is the difference between their y coordinates, or x squared. And then the last and extremely interesting thing that we have to figure out is, what is this point right here where these two curves cross? Well, it's the curve y equals 1 crossing the curve y equals x squared, and we can do the algebra like we did before to figure out where y equals 4 crosses y equals x squared, but we can probably just see that that happens when x equals 1. And so the x value right here is 1, and that's the point where the inner radii change, where the length of the inner radius changes. In other words, the inner radius is 1 for x values less than 1, and x squared for x values greater than 1. And that tells us all we need to know in order to set up our expression for the volume, which is just this. It's the integral from 0 to 1 of pi times the outer radius squared, which is 4 squared, minus the inner radius squared, which is 1 squared, with respect to x, because x is our variable in this case, plus the integral from x equals 1 to x equals 2 of pi times the outer radius, still 4 squared, minus the inner radius squared, and from between 1 and 2, the inner radius is x squared, so that's where the x squared comes from. And then those are both easy integrals, and there's plenty of arithmetic to do, and in the end, you should get 124 pi over 5. Okay, that was our last video on volume. You probably noticed that I introduced two slightly more complicated concepts than we have seen before. Watch it twice if you need to. Practice makes perfect. There is, of course, yet another homework on volume to try, so take a stab at that, have some fun with it, and I'll see you in class.